Your system has thousands of files that are neatly arranged inside separate folders, and these folders can be nested inside another folders, creating a hierarchical tree-like structure. But your disk does not know what a folder or a file is. It only knows how to store data in blocks of bytes. So, how does the OS turn your hardware into hierarchical file system that we are used to using? That's what we are going to understand in today's video. Let's get started. Let's understand what a file is first. A file has two parts, the actual data and the metadata about it. The actual data in the file is stored in a data block, and the metadata lives in a separate structure called an inode. Inode stores data like size of the file, timestamp, owner, permissions, and a pointer to the data block. A file also has a name, but it lives inside the data block of the parent directory, and it points to the inode number of the file. Moving on to the directory structure, directories are not special containers. They are also files whose data blocks hold a table mapping file names to their inode numbers. The entire file system is arranged as a tree where directories are internal nodes and the files are the leaves. Path resolution works by working this tree from the root node, one node at a time. And the root node is always inode number 2, that's hard-coded, and which is how the OS always knows where to start. Let us take a path /home/user/file.txt as an example. We will start from the root node, go to the home node, and then the user, and finally we will reach file.txt. Let's talk about hard links and symlinks now. Since file names are stored outside of the inode, we can have multiple file names pointing to the same inode number, and this is called a hard link. Under the hood there is only one file, but multiple names are pointing to that one file. The inode keeps track of the reference count, meaning how many different names are currently pointing to this inode number, and the actual file only gets deleted when all of its references are deleted. Hardlink have two constraints. They can only exist on the same file system, and they cannot point to directories. Symlink, which is short for symbolic link, is different in the sense that it's a brand new file with its own inode number whose content is just a path pointing to some other file. The OS follows that path every time the symlink is accessed. If the target path is deleted, the symlink breaks and you get a dangling symlink. Symlinks can cross file systems, and they can also point to directories, unlike hard links, which is why they are often used for things like versioned binaries. For example, if you have a path like user/bin/python, which points to /user/bin/python 3.11, so when you upgrade your Python version to some other version, you just need to update the symlink. Let's talk about how data is actually stored at the hardware level. A file system divides the disk into 4 separate regions. First, superblock. Second, inode table. Third, data blocks. Fourth, free space bitmap. Superblocks come first. It holds the metadata about the file system itself, like the total size, the block size, how many inodes are allocated, and so on. Inode table is a fixed size array where you get one slot per file. Since the array is a fixed size, you can run out of inodes even though you have free disk space available on your system. Data blocks are where we store the actual content of the file. They are typically divided into 4 KB blocks. Free space bitmap tracks which blocks are available. 1 bit per block is used to mark this. 0 means that block is free. 1 means it is being used. The file system needs a way to allocate data blocks to a file, which we will cover under file allocation strategies. There are 3 approaches for the file allocation: contiguous allocation, linked allocation, and indexed allocation. Contiguous allocation allocates all of the file blocks in a row on disk. This is great for sequential reads, but files cannot easily grow, leading to disk fragmentation over time as files are created and deleted. Linked allocation has each block containing a pointer to the next block. This solves the problem of fragmentation and your file can grow easily, but to jump to the middle of the file, you will have to start from the beginning of the chain, which is very expensive. Indexed allocation is what most real systems use. The inode holds an array of block addresses directly, so you can jump to any block in constant time and there is no fragmentation. Now imagine that you are writing to a file and you get a power cut in the middle of it. How does your file system handle this problem? Journaling is the solution which file system uses. It works like this. Before you apply any changes to the actual file system structure, the OS writes the intended changes to a separate journal area first. Only after that log entry is safely written does it apply the actual change and mark the general entry as committed. On recovery after a crash, the OS replays any journal entries that were written but never committed or discards ones that were incomplete. Either way, system ends up in a consistent state. If you have worked with databases, this idea is exactly similar to write-ahead logging or val files. Let's talk about some common file systems. ext4 is the default file system on most Linux systems. It is journaled, very mature, and has been the standard for over a decade. Next is NTFS, which is the Windows file system. This is also journaled. It supports ACL based permissions and you can create very large files using this. Next is APFS, which is Apple's modern file system. It uses copy on write instead of journaling, supports snapshot, and was specially designed for SSDs. Next is FAT32 and exFAT. They are simple. They do not have any journaling support, but since they are universally compatible, that's why USB drivers and SD cards use them because any operating system can read them. tmpfs is very interesting. It is a file system that lives entirely in RAM. There is no persistence at all, and it is generally used for temporary files on Linux. This is very fast, but since we are storing everything in memory, all the data is lost on reboot. All these file systems that we just looked at have completely different implementations. So how does your application code call or interact with these file systems? Does your application need to know the interface for every file system? The answer is no. There is a concept called virtual file system which simplifies things for an application developer. Virtual file system is a kernel level abstraction that sits between your application and the actual file system driver. Your application makes a system call that goes to your virtual file system, and the virtual file system forwards that code to the appropriate driver. Your code does not need to know the actual underlying file system at the hardware level, and you get a consistent interface to interact with the file system. Virtual file system maintains a mount table, which is a mapping of a path in the tree to the file system driver, which handles that path. When you access any path, the VFS looks up this table to figure out which driver it needs to call. This leads to our next concept, which is bind mount. A bind mount adds a new entry to that mount table, but instead of pointing to a new file system driver, it points back to a directory that already exists in the tree. So the same underlying data is now accessible from two different paths and no files were copied. This concept is heavily used in Docker to map a directory from your host machine into the container. It is a bind mount at the VFS layer. That's it for today's video. I hope you now understand all about file system management in OS. If yes, then please do like this video and comment down if you have any questions or if you want me to cover any other topic. Subscribe for more such content. See you in the next one.